Hello everyone, my name is Alexander and I'm a freelance developer. The most of my projects in recent time were related to 2D and 3D programming using standard Apple frameworks and OpenGL and Metal, as well as mobile application optimizations on iOS and Android. This talk is about creating standalone music apps with 3D UIs on iOS using built-in Apple SceneKit framework and open source and free AudioKit framework. My interest in creating music instruments with 3D UI started when I began to make applications that imitates a hand drum for iOS. Hand drum is an idiophone class instrument. Hand drum and its descendant hand pan. And it resembles an UFO in its shape. This is often referred as a meditative instrument and used in art therapy sessions. And in order to achieve more immersion into the experience playing the instrument, there are basically two main possibilities. The first is to add high-quality samples of a real instrument to the application, and the second one is to add 3D interface that with a model of a real instrument. So it looks something like this. And an outline of this talk. First, I would like to introduce Apple SceneKit framework, give its overview of its main features, and 3D programming in general. Then I will talk about developing a 3D UI using SceneKit. It includes creating basic synthesizer components like faders, rotary knob controller, LCD screen, and piano keyboard. Then the next topic is adding audio support using AudioKit. And a quick introduction to MVVM, architecture pattern, and RX Swift. This architecture is used to achieve separation between business logic of the application and presentation logic, and to improve testability of application logic. And then there will be I would like to describe an example synthesizer project with 3D UI. This project is available at the in the following repository. The content of scene in SceneKit is rendered in three different types of classes. The first is a CN view. It's a basic standard SceneKit view. It represents the area on the screen that draws SceneKit content. The second type is AudioKit SCN view. It's the same, but it's controlled by AudioKit world tracking. It's very similar to SCN view and uses the same scene that SCN view uses. And the third type is SCN renderer, which allows to draw the content of a scene in a metal context or OpenGL context. But OpenGL is deprecated. So we will discuss the SceneKit only in relation to metal. All these types of use implement a SCN scene renderer based protocol. SceneKit implements a tree-like hierarchy. At the root there is a scene renderer, which is one of those three types of view. Scene renderer owns a scene, which is a root tree structure that contains a tree of nodes. So it's the root node, and it contains references to child nodes, child SCN nodes, and each node has a weak reference to its parent. By default, an SCN node is simply a 3D transformation in 3D space. So it represents a system of reference in 3 dimensions. It also can contain a reference to the camera object, to light, and to mesh geometry. Geometry in its turn contains a reference to materials that influence the way how the geometry is rendered on the screen. And there are two basic types of camera. First is perspective projection. It imitates perspective view with perspective, and orthographic. It's a plane projection. There are different types of lights that are supported by SceneKit. Ambient, point light, directional, which simulates sunlight. There is a spotlight, which also has a direction, like a directional light source. There is also iOS photometric profile light source. It can be thought of as an advanced spotlight. There are numerous photometric profiles available on the web, which can be loaded into the scene, and mostly used in architecture and such applications. SceneKit supports various types of materials. First one is a physically based material. This type of lighting model represent physically correct type of rendering, and there are also classic type of materials like Fon, Blin, Lambert, and constant shading. Constant shading, in a constant shading mode, the color of is simply constant, and also SceneKit supports various types of custom render, custom extensions to the lighting model using metal shaders. SceneKit coordinate system is a 3D coordinate system with X, Y, and Z axis. The camera is positioned at plus Z direction and looks toward minus Z. The coordinate system is right-handed, the same as in OpenGL and Vulkan APIs. Coordinates are homogeneous coordinates. In addition to X, Y, and Z, there is a W coordinate which is used to represent transformations in a uniform way, so that scale, rotation, and translation could be represented by a 4x4 matrix. If when using the first three coordinates only, it is not possible to represent a translation by a matrix in three-dimensional space. Each SCN node has following properties that represent its transformation is in 3D space. The first is transform. This is 4x4 matrix. It combines information about translation, scale, rotation, also about projection, but projection is handled by SceneKit internally, and you don't need to think about it in SceneKit, because it's already handled in the most situation. A position is a this is a node translation relative to its parent node. A scale is simply a scale, and rotation. This is a 4 vector. The first three values is a direction, a normalized direction of an rotation axis, and the fourth value is an angle of rotation about this axis. There are also Euler angles, which is a float 3 vector, and it contains pitch, yaw, and roll. Its rotations about x, y, and z axis correspondingly. And these three rotations are applied in reverse order. So roll, yaw, pitch. And orientation is rotation as a quaternion. Quaternion, its benefit over the 4x4 transformation matrix that it is possible to linear interpolate quaternions. 4x4 matrix is could not be interpolated, and transform property is not animatable in SceneKit. All other properties like position, scale, rotation, Euler angles, and orientation are animatable. This means that SceneKit can smoothly interpolate between two values. When one of these properties is changed, this change is reflected in the other properties. This slide shows how the transformation is applied to a four-dimensional homogeneous vector. And there is a translation, how a translation matrix looks, scale matrix, and combined scale plus translation. This is rotations about 3 axes. There is one more property that is useful in describing the node transformation in space. It's called pivot transform. It's a 4x4 matrix. All other transformation properties are computed relative to this transformation. If a pivot transform contains a translation to some point, then all the rotation and scale and translation of the node will be relative to that point. And that point is called pivot point. There is an example of the use of pivot transform to simplify node transforms manipulation. In this example, there is a sphere lying on a plane. It touches a plane in a single point. And in the code below, first two lines we create a sphere geometry of radius 1, then create a SceneKit node and pass a geometry as one of parameters. Then a plane is created. Then plane is rotated so that it, because in SceneKit the plane geometry looks towards z axis, and by applying these Euler angles to the plane, it is becomes a horizontal. Then I set a sphere pivot transform to a translation to point O minus 1 O, which is the lowest point on this sphere, and sphere position is set to 0, and since it's computed relative to pivot point, it looks like on this figure the result of execution of this code. Another example of use of a pivot transform is for creating a turntable camera control. There is a perspective viewport and a view from the camera. And it operates like on this video. There are at least two possible approaches to implement this turntable camera control. The first is based on spherical coordinates. There are two angles in spherical coordinates system. There are two angles. The first describes the elevation, and the second is the rotation in x-y axis. In order to transform a coordinate from a spherical coordinate system to Cartesian, you can use the following transformation below. In a spherical coordinates-based approach, we need to set both a position of a camera when the camera moves and its Euler angles, because when position is changed, the camera must point at the center, and its Euler angles need to be updated as well. The first function is the pen gesture recognizer callback. It interprets a translation in a view and updates camera. It computes the new angles, new Euler angles of camera, and updates camera. And this is function that resets camera positions. It uses a CN transaction block to make the animation and not to perform the reset instantly, but smoothly. There are three viewports. First one is perspective, and top viewport, and a view from camera. In this approach, the results looks like this. You can see that when camera moves from one position to the other, the orange sphere must stay at the center in the camera viewport, but it goes out of viewport because two parameters are animated: position of a camera and its Euler angle, and the camera moves not as intended. This can be fixed using a pivot transform. In this implementation, only camera's Euler angles are modified when in a pen gesture recognizer callback. And the result of execution so in this case, camera always looks at the center, and the animation is properly implemented. So the pivotal transform could be intimidating at first, but it allows to implement many transformation-related tasks more elegantly, and it will be easy to support the code. Okay, the next is physically based lighting. There are two physical parameters of materials that are supported by SceneKit in addition to standard diffuse color. The first is the metalness of material. It varies from 0 to 1, and roughness. This figure depicts the dependency between material appearance and its metalness and roughness. Okay, let's go to the. These are the built-in parametric shapes that are available in SceneKit. So it's plane, box, sphere, pyramid, text, and capsule, tube, and torus. It's possible to create a custom mesh geometry. The first way is to import geometry into a Xcode scene editor. It's a visual editor that allows to build a scene and to add animations and to set up material properties. The second one is load mesh programmatically from supported file formats. And the third option is to create geometry by hands from its index elements and vertex attribute sources. There is one pitfall when creating geometry programmatically, is that elements indices must have index types or fixed size. U in 16, U in 32, or U int 64. Because standard int type in Swift has different size on different platforms. On 32-bit platform, it has 32-bit widths, and on 64 bits correspondingly. So scene geometry class contains references to multiple elements, geometry elements, which could be triangle, strip, lines, or points. And it contains references to vertex attributes, which are positions, normalis, texture coordinates, and so on. The second, another topic which is very important when building 3D UI is heat testing. It is used to test when user taps a screen. It's used to test for intersection with geometry, with some mesh. And a scene renderer protocol implemented by SceneView and AudioKit SceneView supports heat test method. It finds elements located along the array, which is directed towards minus z direction. And there are also other options, other methods, but they are less useful when creating 3D UIs. And heat test method, it accepts options parameters, and there are several options that can be used to control the behavior of heat test. And the most useful one in creating 3D UIs is the Boolean property bound in box only. It when this property is set to true, the intersection with bound in box only is checked. When the geometry has a complex shapes and a lot of triangles in it, checking for intersection could take a long time and require many computational operations with floating points. Another one, in ignore hidden nodes. It's by default set to true, and sometimes it's useful to add very simple nodes that low polygonal modes that represent the item geometry, and hide these nodes and check the intersection with those nodes. Okay. Heat test function returns the array of SCN heat test results. The most important of the properties is the node that has been touched, and geometry index of a triangle. There are different options to animate SCN contents, and the most of properties of nodes and materials are animatable, only matrices are not. The first option to animate is to animate in SCN scene renderer delegate callback. This is an explicit type of animations, and is performed on a per frame basis. The second option is implicit animations using an SCN transaction. Actually, every change to parameter in SceneKit is wrapped in an SCN transaction implicitly, and a developer can create also nested SCN transactions explicitly. Also, as SceneKit uses a core standard core animation classes for its animation, and playback is controlled using SCN animation player. This is an example of using a SCN transaction block which bundles changes to two parameters at the same time. This is an example of per frame animation. Next topic is power consumption and its how it is influenced by the visual quality. Any change to the scene graph leads to a redraw on the next next call to a scene renderer. Also, anti-aliasing affects power consumption. There are two options in SceneKit and in Metal on iOS. Multisampling is limited to 2x and 4x, which is not enough to completely eliminate aliasing, and aliasing is still present in a high-frequency visual contents. To achieve better image quality, one can use oversampling, but it's very expensive. One can add an oversampling by setting a content scale factor of our scene view. To value 2, 3, or 4, and shadows are very expensive in SceneKit. Okay, let's talk about AudioKit. This is an example when first we create an oscillator using a key oscillator class, then add a filter, and a filter takes oscillator as an input. Then a reverb is added to the chain and connected to dry-wet mixture, which allows to set a balance between dry and wet signal. Then we add a gain. It is implemented by a K-booster class. And there is a microphone which is connected to the filter, to low-pass filter, and to a gain. In this case, the connections are made using arrow syntactic sugar. Then output of AudioKit main class is set to a mixture that mixes a signal from an oscillator and from a microphone. And the last line starts the processing. Oscillator nodes started using the start method. I think I'm running out of time, and I would like to show an example project. This is a SceneKit scene editor file which contains a scene and all geometry for this application. It contains a synthesizer node which contains a keyboard. Each keyboard is represented by a separate key mesh. There is a fader node, root fader node. All faders are attached to this node. There are 4 faders, and this root fader node is rotated so that when the Z position of a fader is changed, it moves moves along this along its path, and there are rotary knobs and LCD screen. Okay, let's build it. While it's building, I will set up a screen mirror. And this is how it looks built. It supports a parallax effect. So when the application subscribes to gyroscope updates and gyroscope rotation rate along X, Y, and Z influence the rotation of an object, of a scene. So when I touch the fader, it changes the value and it's reflected on an LCD screen. The tuning setting is not standard 12 temperament scale. It's 19 temperament scale. It's used because AudioKit supports various types of tunings. It supports various types of equal temperament scales. You can pass any number of tones, integer number of tones, and it also supports different just intonation scales. The project contains a synth model class, which model of the synthesizer. It contains filter, cutoff, resonance, amplitude, and envelope information. There is a view model which contains business logic of the application. It uses RxSwift to output parameter changes to presentation classes. There is a struct output which contains an observable variables which presentation classes can subscribe to. The properties reflect the model, this synthesizer model. These functions, set amplitude, set attack, and set decay, are for presentation classes to propagate the changes initiated by a user in a UI. So the architecture is MVVM. View here owns view model. And view model publishes changes to its parameters via its output structure. View observes the changes and propagates changes from a UI to view model. The UI is dual. There is a main view controller that creates 2D UI kit view and 3D SceneKit view, which all reference view model. On this application, a user can switch between 2D, standard 2D UI and 3D one. Sound, the code that is related to sound generation is implemented inside a synth engine class. In its init method, it loads a wavetable. It's done using a table class. Then a polyphonic oscillator bank is created. This class allows to create a polyphonic sound. And the signal chain is this. This synth engine class is owned by a view model. That propagates events to synth engine. And view model is owned by main view controller, which creates a view model and view classes. And it's a very simple class. It's only responsibility to set up UI and set up view model and pass view model to presentation classes. View controller 3D is a presentation class for a 3D view. It sets up the callbacks. It subscribes to the changes in view model in function setup Rx. It adds callbacks to be called when any of the model parameters changes. And based on values of these parameters, it modifies the transformations of knobs. In case of faders, it modifies Euler angles. It modifies rotation of a knob about that axis. And in case of fader, it influences the position of fader. Okay. So, okay. Any questions? Please.
Were you able to? So I saw you had both a 3D view. You were able to switch between a 3D view and a 2D view of controls. Are you able to overlay those two types of views? So, for example, if you had some 2D controls with a 3D element behind them within the same view.
I mean a transparency-like effect.
Yeah, or just having can those two can the 3D controls live in the same view as 2D controls, or do they have to be separate views?
There are two possibilities. The first one is simply arrange views such that 2D view is below 3D view and add a transparency to 3D view. And the second option is to take snap in a 3D view, so it will be a part of the scene itself.
Thank you.
All right, I think we need to wrap up because we've got a keynote now, so thanks very much.
Okay, thank you.